Hello, 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 Chastity. Hello, Vanita. Ooh, that's a new. Ooh, Gengar. Hello, Yanelli. I believe it's Gengar. Okay, hold on. I won't get. Okay, hold on. Wait. Chat. Sorry. Good afternoon, Gabriella. Wait, I see Gabriella in the chat, but where? Oh, I see. Okay. And good afternoon, Kaya. I see you in the library as usual. And good afternoon, Vanita. Wait, did Vanita? Okay, sorry, the things are moving around. Good afternoon, Carlos. Good afternoon, Genesis. Good afternoon, Ariana. Good afternoon, Chastity for the double. Good afternoon, Brian. Thank you for asking. Well, thank you for asking. I have a more detailed answer on that in a second. Good afternoon, Yaneli for the double. Good afternoon, Mariam. Good afternoon, Natalie. Okay. Um, and good afternoon, Annie. And good afternoon, direct. Okay, was one. I mean, not that. Okay. Oh, good after. Okay, couple. Good afternoon. Okay. Um. So wait. So a couple of people are asking me about my break, which is very nice. Well, I hope you guys had a break. I do understand that if you're a science student, it's often you off breaks are breaks, and that's also true for science faculty and people with children. Um, but it's very nice of you to ask. So I hope you guys had a good break. Oh, wait, hold on. Okay, no, so it's. I want to get to physics, but it's nice of you to ask me about my break. The one thing I have to say about my break is to issue an apology that you may not be. Uh, so I'm not done with the exams yet. Some of my break I did spend with family rather than catching up on the work that I wanted to catch up on. But then I did start, you don't care about all these details, but I made a lot of mileage with the exams. A lot of them are done, but a lot of them are not done. And that by that I mean across all of the sections. So the machine is going, I apologize if you still have not gotten an exam back, and you probably have not if you're in this class, even though this is the class where all of you handed them in on time. I'm very aware of that. Uh, and perhaps should have done this section first, to be honest, because of that, but I didn't. Um, so your exams are still in progress and are still coming back. And they will. I apologize. I won't dwell on all this period. Some of you may have already gotten yours back in this section, but probably not many of you. So I'm just going to be returning them as I do them. They are taking a while. I apologize. They are happening. You certainly will have them in time to do things that you need to do for the final exam. And the small consolate, it's not really the small um, recognition of that fact also is that the next homework, which is the last homework number 7, the Gauss's law homework, I've rescheduled as of this morning. I changed it in Google Classroom, I believe, so that it should now be due not this coming Wednesday as it was, but a week from this Wednesday. And if you don't get if you and you should have your exams by then. If you don't, if some of you don't, then I'll push the homework again, but I don't think it'll come to that. It shouldn't come to that. I mean, you really should have your exams by then. You should and you should. Um, that homework is intense. It is the most challenging of all of the homeworks for sure. And it is the last one. Again, I'm talking about homework 7. We will start the concepts that you need for it or help that you need with it. Everything we are talking about from here to the end, in a sense, is related to that homework. And we'll start that discussion today. So, in other words, there's no new homework for a while still. If you want to be doing anything for physics, then be catching up like I'm trying to do for you or with regard to you. Um, So again, for anybody who just joined, I still don't have many of your exams. I apologize. I said I was going to try to catch up and finish over break. I did do a lot of catching up, but not enough. So you will get them. Uh, and and I do understand that it's annoying, to put it mildly. But again, also just to repeat for anybody who just joined now, homework 7 is not due in 2 days. It's due um, in a week and 2 days. And obviously you can still, and I'm noticing, again, I'm very behind. I'm catching up, but I am noticing, I do see every time someone submits an old homework or a revision of an old homework or something like that, I'm certainly tracking that mentally. I'm certainly aware of it. And obviously it all gets time stamped and it all gets stamped in Google Classroom and all that. Anyway, all right. So I want to go on with the material now. Um, so I will. So I will. Yes, we're going back to electrostatic fields. Um, what's going on this front board is a quick sketch of the transition from electrostatic field vector representations to a visual representation known as electrostatic field lines. These two pictures on the front board don't look that different, but they are different in some subtle ways. And the main point of today's discussion is to unpack what the difference is between these two pictures. Again, so we're going to transition today from electrostatic field vector diagrams to electrostatic field line diagrams. Sounds like a technical thing. It is a technical thing, but it's actually a very big deal. So it's more about electrostatic fields. And as one more moment of background, and this will be, as I say, this is all to build up the concepts that we need for homework 7 and for the end of the semester. One more quick bit of perspective on this or background on this. The whole concept is electrostatic fields. That's what we're talking about right now. Last week or 2 weeks ago before break, the very last problem that we solved, which was homework 6, which of course you was due then, but you can still hand in and all that stuff. And also just sidebar, I'm sure this is clear. Well, hopefully this is clear to you or you gathered last semester if you had me. Like, the farther behind I am and the deeper you are into the semester, the more I recognize and am sympathetic to how far behind some of you might be. In other words, please, even if you haven't done the last homework, it will be very beneficial for your final exam. And yes, I certainly will accept it late, to put it mildly. Like I'm a little bit, I can only be so rigid about lateness at this point if I'm taking this long with your. So the last homework was in principle due 2 weeks ago, but you certainly could still hand it in. And if you were with us right before break, you'll know that we pretty much walked through, I think, actually the entire assignment as a class. So it wouldn't, of all the things you might want to do for points or for to get yourself mentally caught up in this class, that would be recommended, homework 6. Anyway, what happened in homework 6 was that we computed the electrostatic field at some location, like over here, like the origin of some coordinate system. And we computed the electrostatic field due to 2 point sources that were somewhere in that region that were in the coordinate system. So like there was a point source over here, positive, and another point source over here, negative. And due to those point sources, we computed the electrostatic field at an arbitrary location over here. So what did that mean is, in effect, we added the field vector from one point source to the field vector caused by the other point source. And we got one resultant final vector, at the location of interest, at the origin. Why am I saying all? That's what we did 2 weeks ago. It was a lot of it was a thick computation just to compute the field caused by two dots of charge. Now, that's a lot of work to do to get the field caused by two dots, by in effect, like a proton and a electron. Of course, in the real world, even the simplest bit of material involves a lot more than a proton and a electron, right? Like in the lab, even in a simple scenario, you might have, well, not only do you have things that involve lots of protons and electrons, like even a drop of water, as of course you know from chemistry and so forth. I mean, even a drop of water has a bunch of protons and a bunch of electrons. But let's even be more sort of physicsy about it. Say you're in the lab and you're looking at a wire, a line of charge, okay? You a line of charge would be a bunch of dots of charge, not only many, many dots of charge, but so close together that in effect, they are infinitely divisible from one another, right? A wire constitutes, like I say, a line of continuous charge rather than a set of discrete dots of charge. So what we want to be able to adapt our notion of fields. We want to be able to adapt and apply it to situations of continuous charge distribution. And we want to be able to do it in a manageable way. So I'm about to flip the page on the notes, obviously, and in fact, change the view on the screen. Where I'm going with this, what I'm trying to say is, in principle, the field at any given point in space, due to a bunch of charge somewhere else in space, the field at a point in space should be the sum, is the sum of all the vector contributions dictated by Coulomb's law from each dot of charge surrounding that location. In other words, once you can add two field vectors like we did 2 weeks ago, in principle, you could add 3 or 4 or 5 or 6. And in principle, that's all that's happening when you get the field from any kind of situation, no matter how complicated it is. All that's happening is a vector sum of a bunch of Coulomb's law contributions. But if that's the only way that we can actually solve the problems, by literally adding up a bunch of Coulomb's laws or even integrating a bunch of Coulomb's law vectors, that's going to be an unmanageable amount of work, computation. So there's got to be, well, so there, we hope there's a more manageable way to zoom out and look at continuous charge distributions. That's where we now start to look in physics, is continuous charge distributions. So the question is, ultimately, the question is, how do we analyze and compute the electric field due to a continuous charge distribution? But the first question is, how do we visualize it? So, okay, so this board, it just summarized what I just said. We're now moving to continuous charge distributions, and what kind of electrostatic field they produce. And it's all a big expansion of Coulomb's law, which is off here to the right in blue. E equals 1/4 pi epsilon naught times Q over R squared R hat. So that's what topic we're moving to here. There was one quick thing I was just going to say. So the summary of everything I just said inefficiently is the central question of all of electrostatics is, given a bunch of charge over here, what is the electrostatic field over there? That's what it's all about from here on in. If you have charge over here in some formation, some distribution, some arrangement, some shape, a bunch of charge over here, ultimately, what can we say about the magnitude and direction of the electric field produced at some point in space over here? Okay. So in order to do that, we first have to talk about how we visualize this before we even get into computations, okay? So I'm going to remind you that the way we've been visualizing field up until now is with vectors. So this picture is a reminder of it's a vector field diagram from a positive point source, like plus Q, right? So like a proton. So if a proton is sitting somewhere in the lab or somewhere in space, like at the bottom of this picture, I could draw a bunch of arrows everywhere. And I could draw a I visualize in my mind that at every single point in space, there's an arrow sitting there. Like what a field is really is a vector valued function. The input of the function is point in space. The output of the function is field vector, magnitude and direction of force waiting to happen. Force per charge, right? Newtons per coulomb. So the idea is when I draw a vector field diagram, I'm drawing a bunch, just enough arrows to represent what the pattern of arrows is. Like this is just like a slice, a cross section, like a I don't know what my problem is. This is a sample of the arrows. The idea is no matter where you are in space, there is some arrow sitting there conforming to this pattern. And what is the pattern? The pattern is that, first of all of the arrows are pointing away from the positive source. The idea is like if you, oh yeah, okay. If you pick a point in space, point P, like we did 2 weeks ago, a location of interest, or what some people call a field point, you pick a point P. To ask what is the field at point P is to ask what is the magnitude and direction of the force that would act or could act on a test positive 1 coulomb of charge that could be sitting at that blue point P, right? Again, to overemphasize this point, like point P is just a location in space where I want to know what the field is. Field exists at every point in space. To talk about the field is to talk about the force per charge, the force that would act on every positive 1 coulomb of charge that could ever arrive at that location. Like the field is there, whether the test charge is there or not, right? And the whole idea is the field is the force per every 1 positive coulomb of charge. So if it turns out that there's 2 coulombs of charge there, then on each one of those coulombs, there would be that many newtons of force. So the total number of newtons of force that would act would be 2 times whatever the field is. You follow? Okay. And so if I consider that blue location of interest, point P, I notice that there's a white small arrow pointing to the right there. Like I'm at the tail of a small white right pointing arrow. What does that mean? It means that if I were a positive 1 coulomb of charge at that location, I'd be shoved to the right. Why shoved to the right? Well, because I'm positive. By definition, the test charge is always assumed by convention to be positive. And apparently the source charge here is positive, right? I'm drawing the field arrows from a positive Q. So positives push on other positives and they push along the line that connects the two, right? So if I'm there at location P, I'd be shoved to the right and I'd be shoved a certain amount. What amount? Well, if there's a scaling factor for this diagram, I could tell by measuring the arrow at that place. Now, but I could tell, even if without making any measurement, I could see comparatively that the amount that I'd be shoved to the right is a lot less than I'd be shoved to the right if I were closer to the point source, right? In other words, I'm taking way too long to say that all the arrows from a point source from a positive point source point away from it, and they get smaller and smaller as I get farther away, right? And that's what you want to picture when you're picturing vectors. A field is a bunch of vectors everywhere pointing in certain directions and of certain lengths. And if the source is one point, then the vectors get shorter and shorter as you get farther away, and they point out if the source is positive. If the source is negative, same pattern, only they all point in, right? They all point in because a source could be anything. A source could be positive, negative, could be big, could be small, right? The source could be anything making the field. But what the field is a prediction of what force will be exerted on a positive 1 coulomb of test charge. The test charge is always positive. I didn't get this when I was in college. I don't know why. You probably do, and I'm probably overemphasizing the point. But for some reason, it never sank in with me that the test is always assumed to be positive. So the sources push out, and so positive sources push out and negative sources pull in. It's all about what would happen to a positive. All right, I've said it enough times. But notice, as far as magnitude, it's the same thing either way. The arrows get smaller and smaller, shorter and shorter as you get farther and farther away from the charge. Okay. Now, like all vectors, this is a rough sketch in the sense that I just drew enough so that you could see the pattern. But it's not rough in the sense that if I actually picked a scaling factor, if I said each arrow is going to be 1 millimeter in length for every Newton per coulomb of force that it's meant to represent, then I could use these arrows as an actual computation tool, right? If I were drawing them precisely enough. So they're serious. They're not just rough ideas. Okay, that's the vector way of thinking about fields. Again, the summary of everything I just said, is if you're trying to picture what a field is a bunch of arrows in space. The minute you put something in space, it produces a bunch of arrows everywhere in space to say wherever you are in space, you'd be pushed or pulled in a certain direction in a certain amount by whatever is in space. So let me put it one, right? So picturing fields this way, and again, we're not saying that nature literally has like arrows sitting there in the air, but we are saying that nature involves information being spread everywhere out in space. Like each one of these arrows represents information, magnitude and directional information that we believe is in space the minute there is stuff in space to produce that information. I mean, that is an important distinction. The arrow is a way of picturing it in our mind, but what we're trying to picture in our mind is that if there's a proton over here, then whatever point you are in space over there, it's somehow understood. Like space over here knows that there's a proton over here. It knows that if another proton comes, it will be shoved in a certain direction with a certain strength. So that's what these arrows are meant to represent. Now, it's a lot of arrows to picture in your mind and a lot of arrows to draw just to picture the field situation from one point. So it turns out there is a more efficient, smoother, simpler way to picture these things that's more applicable to once we get to smoother, more complicated situations. What we do is we sew up all the arrows into what we are going to call field lines. Okay. And this is important. Now, this is a different, just like, you learn about graphs in 7th grade and then you learn about vectors in 11th grade or whatever, different ways to represent information. We're now going to start thinking of this same information, but we're going to represent it and then visualize it in a different way. So imagine all of these arrows being sewn together into lines. Then you would have a picture, if you sew up the vectors from a positive, you'll have a picture that looks more like this. Now it doesn't look that different. Right? I mean, I cut down the number of arrows, like, by 67%, right? So that actually is a big deal, but you can imagine if the situation gets any more complicated than just one dot, the savings on this is going to be bigger and bigger and bigger. what I did was connected up all the arrows, and then I shoved the arrowheads into the centers of the lines, or so, right, to make a very important point, which is that once I sew up these vectors and call them lines, they are, in fact, no longer vectors. What I mean by that is we're trying to convey the same information. So we're now making field line diagrams. This is the field line diagram from a positive Q point source. Doesn't look that different. You'll see how it gets different in a second. But one big difference is by moving from vectors, from vector arrows to lines, I'm getting rid of the notion of length. Like where it says at the bottom right here, these are no longer vectors. By that, I mean they're no longer, it is no longer the case that the length of one of these segments indicates magnitude. In fact, these segments no longer have length at all. What do I mean by that? Well, yeah, what do I mean by that? In order to show you what I mean by that, I'm going to switch screens. I'm going to bear with me for a second. Oh, hold on. I had it, but I don't anymore. One second, one second. Okay. Okay. This is probably like a copyright violation, but so here, all I've done is I've just, as you could see, I just typed EFieldLineDiagrams into Google Images, and we get all these fancy pictures, and pictures can get a lot more fancy than this. Right? I mean, these are E-field line diagrams from various different types of situations, like a positive source near a negative source, two positive sources near each other, a negative and a negative near each other, or a positive of one magnitude near a negative of a different magnitude. And eventually, and I'm going to talk about them. I mean, I just want to give you a sense right now of how elaborate and pretty these pictures can get. Right, they can get pretty elaborate, as you can see. Um, uh, but they can also, right, even for example, here, sometimes they can get really simple, like this can you see? On the one hand, they get elaborate, even when you're just depicting the field line picture of, two nearby point sources. But notice, wait, before I go any further, I mean, and this is what we want to talk about is these field line pictures. I don't look, and depending on who you are, looking at them, you might be intrigued and they might strike you as sort of beautiful as they do now to me. Or if you're like the way I was when I first saw these things, and I still remember when I first saw field line diagrams, um, I was totally intimidated by them. I mean, I thought they were cool looking, but I was like, okay, there's no way I could ever really actually make one myself or understand what the heck these things are supposed to be conveying. So if you feel like that way at all, bear with me. I think it's not true. I think you totally can. But that is definitely the way I felt. But I want you to notice, like, on the one hand, they look like they're getting very elaborate, like this one here or this one, if you see where my cursor is, right? On the other hand, I want you to recognize that everything we did 2 weeks ago, remember everything we did 2 weeks ago, which was an analysis of just two dots, right? Just 2 points. All the computation we did was to get the one vector arrow that was sitting at one location at the origin due to those 2 points. If you remember, I'm not going to like change the screens right now. If you remember, so we never, um, like what I'm trying to say is we just had two dots 2 weeks ago, and we did all that work just to get one arrow resulting from those two dots. At the beginning of our analysis, I did draw the field vectors from one dot, right? And I put it in the graph. And then I put a bunch of arrows from the other dot and I put it in the Cartesian coordinate system. And they were kind of near each other. And it made the diagram very crowded. You might recall, like one was sort of in red and one was in blue or something like that. And there was a bunch of arrows that made the diagram pretty crowded. And I had to stop. I couldn't add anything more to that diagram. And that was a bunch of arrows. That was just the arrows from one, some of them, and the arrows from the other. It wasn't even an attempt to get the resulting arrows everywhere in the coordinate system. Do you see what I'm saying? In other words, we didn't even try. We just had two dots. We never even attempted to draw a picture of all the arrows that would exist in space due to those two dots. We drew a bunch of arrows from one dot and a bunch of arrows from the other dot. And that was a lot. That was supposed to just give us some sense of what was going on. And then we stopped. And then we did all this math to get the sum of one arrow with another arrow at one location. And our final answer told us what one arrow would look at like at one location. Okay. What I'm trying to say is now, imagine if we wanted a picture of what of all of the arrows, if we wanted a pattern of what all the arrows would look like in space, in the whole space, not just at the origin, but all the arrows that we would get if we had added the arrows from one to the arrows to the other, that would be, first of all, a lot of arrows. Second of all, it would be like a mess. It'd be very hard to infer any kind of pattern or rhyme or reason from all the arrows. And again, I want to be clear, we didn't even try because the vector's just too many freaking arrows and it's just like too intimidating. So what we're trying to do now is build a method where we could sort of tie those arrows together and stand back and get some sense of what's going on. So honestly, let me start you with, honestly, where to go? Hold on. If you look at, I'm all over the place. Pardon me for a second. Yeah. Let me see if I got, sometimes double clicking gets you to real trouble. And really, I don't even think this is legal what I'm doing, but I'm doing this for academic reasons and with respect to all. I'm serious. This is all with respect to anybody, any companies out there that made these pictures. So look at this picture. You can see, right? Yeah. This picture on the board right now, this is somewhat of a depiction of, if you tilted it slightly diagonally, like in our situation 2 weeks ago, we had a positive over here and a negative over here. Now, one simplification, and I'll get to this in a minute. Imagine for a moment if the positive and negative that we had from 2 weeks ago were equal in magnitude. They were not. So that will make a slight difference in this, and we'll get to that in a minute. But imagine if they were equal in magnitude, and imagine if if the whole Cartesian coordinate system from 2 weeks ago was like tilted so that they were just like lined up both on the x-axis. Then all the arrows that the sum of all the arrows everywhere, like if we had done that calculation that we did, but for every point in the space and got an arrow for every point in the space, and then sewed up all of those arrows and connect like all the arrows, that were along certain paths. If we sewed them all up and connected them into lines, then you'd have something that would look something like this picture right here. This is called a field line picture. Now, you see, this is very different. It's connecting up all the vectors in a manner that contains and conveys the same information, but in a very different way. A very different way. I mean, the first thing to notice right away is that these lines curve, right? Vectors can't curve. So these are not vectors. These are sums of vector, like SUMs of vectors. They can curve. They represent the same information. I'm going to tell you how in a minute. They convey magnitude and direction, but in a different way. Okay, they can curve. That's one thing I was just saying. Number two, I keep saying they're not vectors in this, and notice like the arrowheads, they mean something, like they have direction. They have these arrowheads, these tips, if you like, but the tips aren't tips anymore. They're not at the end of the lines. Like, why not? Because what we're trying to get across very emphatically is that these lines don't have length in any significant way anymore. Like, like some of these lines, does this cursor? Yeah. Like this line may look, can you see the cursor? Yeah, you can. Okay. Like this line like looks like it has length maybe, and this line looks like it has length. So why didn't we shove the tips at the end to show that? Because the fact that they look like they have length is an illusion. This where the cursor is right now. That is not the end of that line. That's literally just the edge of the page. Like no joke. The page just ran out or the ink ran out or whatever. So we stopped drawing the line. But the idea that we're trying to convey, and this is why we put the tip in the middle or in some arbitrary spot, is that we're supposed to understand that this line just goes on forever, and this line goes on forever, and this line comes in from forever, if you know what I'm saying. Now, some of the lines don't. Like this goes from positive and it ends at negative, and this one goes from positive and ends at negative. But notice that that's not a coincidence. Like this line here, that's this curved line that's going from the positive to the negative, is longer than this line that's going directly from the positive to the negative. The point is that the length, but they're both clearly doing the same thing. They're both going from a positive to a negative. So the length of a given line does not indicate magnitude anymore. In fact, a line won't have any length at all other than to go from positive to negative or to fall off the page, if that makes sense. Um, I'll repeat that in a better way in a couple of minutes. But um, what else do I want to say about these? We're going to flip back and forth in a second. So we're trying to I know what I was going to say. So there's something in the chat. I'm sorry. It's probably been sitting there for 20 minutes. I'm sorry. Hold on one sec. Oh, wait, that's a really good question. I may have to ask for so Andy's asking, when I say that the lines go on forever, do they stay in the same trajectory or do they also move in place? So I want to say they stay in the same trajectory. If I'm interpreting your question correctly, like uh they would continue, right? Any line that gets cut off, hold on, sorry. Like this, well, right, and I will be more specific about this in a couple minutes, but like this line here, we're supposed to understand really that the page got cut off or whatever, and really this is the continuation of it over here. Like this is heading out from a positive and heading toward a negative, and there's every reason to believe that it will just continue doing exactly that. And then same thing up here, they just like ran out of the room to continue the pattern. But yeah, the pattern, the trajectories continue the same. Now, that doesn't mean that all, like some can literally go off to infinity. Like this one is never going to come back around and actually hit that negative. It will go off to infinity, but it will continue the same way. Is that what you're, the only thing that's confused me about, I mean, tell me if I answered your question, but when you say,
Yeah, I think you answered it. So basically, I was just asking like, because I noticed like the trajectories for like the space when the positive and negative charge are like closer together, like the it's more dense. Like that's one thing I noticed, and I thought like, okay, like do they stay that way, or you know how sometimes like waves or like jet streams like kind of, or like aurora lights, like it kind of like, I don't know how to describe it, but it moves. Sorry.
right,
Like it moves like to the other side. Like I don't know how to describe it, but I was picturing like an animation that I saw like a couple days ago where like it kind of flows, but it also like moves. Also like 3D
Wait,
animation.
wait. So I'm getting, wait, I love it. I'm getting, okay, wait. I love the fact that you're putting dynamism into it, like animation or emotion, is like super cool, but also slightly confusing, at least to me. Right. Okay. And there's a couple of issues you're bringing up, and some of these are going to be easier for me to address once I tell you the strict rules of this. But yes, on the one hand, I mean, you're totally right to make the observation about density. I will address density in a big way in like a minute or two. Your basic thing about the trajectories, right? I want to say, yeah, they continue in the same trajectory. The only the thing that's throwing me off, like if you want to think about animations and stuff, that is super cool. But I also want to caution you that, right, these are not meant to indicate motion of any kind. I mean, if you assuming that the charges that are causing these fields, assuming that the charges are sitting still, which we are assuming, no matter how many there are or how complicated they are, assuming that the charges are sitting still, then the field line picture sits still. And I know you might be doing like a metaphor in your mind, and that's fine. Like you might just be making it come alive in your mind. That's totally fine. But just to be, strict for a moment, if the charges are sitting still, then the field lines are sitting still. And yes, the patterns are according to certain rules, and the patterns do what I think you're expecting or assuming. Um, and I'll even say this, I will say it more clearly in a couple minutes. As far as patterns are concerned, like, yes, when lines tend to be more dense nearby source charges, they will get less and less dense in the pay if you get farther and if you let your eyes wander farther and farther away from the charges, like to the edges of the pages, you will generally find that the lines get less and less dense. Like so in that so yes, I they're not actually waves, like they don't actually ripple on the page. But yes, they do follow certain patterns. Why am I getting tongued? So hopefully that, but I'll say more about that. But yeah, well, I think that answers oh yes, okay, thank you. Okay, I need that so badly. Okay, but now I'm gonna for anybody, I mean, I'm gonna go on and say the things that I was gonna say, but I think they will tend to be elaborations on this answer to Annie's question. Like one thing I want to be clear before I go any further, just like again. What I want you all to realize is that this is a method of drawing and representing, visualizing in our mind situations. It's a simpler way of representing increasingly complex situations. Like again, even the thing that you're looking at, all of you are looking at on the screen right now, it's kind of complex, right? I mean, it's got a pattern, but it's an intricate pattern, right? But please again understand that what this is, and you might say it's kind of complicated for just like two dots. It is kind of complicated for just two dots because the situation in life is kind of complicated from just two dots. But it's a patterned complexity, and this is a way for us to see the pattern. This is the improvement on what we couldn't even do 2 weeks ago because it was too much. This is what happens if you like take all of the arrows that again, just please remember that what this is the depiction of all the points in space surrounding a dipole. Whereas everything we did on Friday was just to compute the one arrow at one point in space from a dipole. By dipole, I mean like a equal and opposite charges, right? Right. So again, I like I get so tongue tied with this stuff, but um, um, these can look intricate. They are intricate, but they're intricate patterns. We're trying, and patterns of what? Patterns of the field that be produced in space, throughout space, due to certain charge distributions. The more complicated the charge distribution, of course, the more complicated the pattern of field lines will be. But once we draw the field lines, well, we're representing the field. But again, what does that mean? Now, this is going to go back to Annie's question a little bit, sort of. To say that we're depicting the field means we're depicting the force waiting to happen at any and every point in space surrounding some charge distribution. So what we're trying to say here with these lines is we're trying to say, just like we were trying to say 2 weeks ago, we're trying to say if you put excuse me, if you chose some arbitrary point in space, some location anywhere, like right here or right here or right here, if you pick some point in space, you want to know what is the field at that point in space. That means you want to know in what direction and with how many newtons would a +1 coulomb of charge be shoved, be pushed or pulled if it were at that point in space. You want to know the net electrostatic force per every 1 +coulomb of charge that could be at a certain location, right? Due to, because of the positive and negative, the 2 points of source charge that are already stuck in space. What I'm trying to say is, and this came up, one of you asked about this in direct chat. Excuse me. But it wasn't Annie. Somebody in direct chat asked last week when we were doing all of our analysis. They asked, wait, is something like they asked, is this what, or they said, what about what one charge is doing to the other? In the problem that we did 2 weeks ago. And it was like a really important, it was a very important question because my big answer was, well, that is interesting, but it's really important that we all see that that's not what we're focusing on right now. In the calculation that we did 2 weeks ago, we were figuring out what is the net electrostatic force per charge at a point in space caused by the presence of 2 point sources. So we weren't looking at how they were interacting with each other. We were looking at how they, as a totality, were interacting with space, how they were producing a force waiting to happen that could happen to like a third object. Okay, same thing here. Same thing here. This picture, I'm not yelling. I'm yelling. I'm not saying anybody has said anything wrong. And this is partly to address, this is just like expansion on Annie's question in a way, but it's what I would have said anyway. I'm saying I want you to understand when you look at these lines right here, and we'll look at others, it's not saying, it looks like it might be saying, oh, things would like move from the positive to the negative or something like that. It's not what it's saying. It's not saying what the positive is doing to the negative. It's saying what the sum total of the positive and negative would do to a third party, to a test charge of 1 +coulomb that could be located like anywhere in the picture. So for example, if there was a test charge right here where the cursor is, which hopefully you can see, or right, no. Will this work? Oh no, wait, no, what? I don't want, oh God, sorry, wait. Okay. I mean to, I'll try one more time, and if it doesn't work, hold on. I just need to draw a dot. That's all I want to do. Okay. Right, like, oh, come. Right, okay. So if you were like, look at that point, if that's like point P, arbitrary location in space, and you want to know what's the field there, well, what you would imagine an arrow closest to the field lines that are already there. Because imagine each one of these field lines is supposed to be a sum. It's supposed to be a sewing up of all the field vectors that would have been there originally if we were willing to draw them all. So you imagine what arrow would be right here, tangent to the curve, right? You imagine, you imagine, oh, sorry. 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 Yeah. You imagine that there's like an arrow there, like tangent to the curve, and right? And that would be the vector right there that would tell you how strong you're being pushed or pulled and in what direction. Like, and so over here it'd be, pointing in a different direction. And how do I know how big or small to make it? Well, that's what Annie was alluding to, and that's what I will say more. Well, I'll say right now, like, like the way you would know if the force is strong or weak is you would look at the density of the lines. All right, let me shift gear. Let me explain that. So I'm going to shift boards. I'm going to go back to my board and explain what I mean about density or why it's important that Annie brought up density. Um, but in the end of the day, what I'm trying to say is you look at any one of these pictures and what they're trying to tell you is what a bunch of vectors individually would, but this is trying to tell you in a smoother, more collective way. It's trying to say that for any given point in space, what direction and how strongly a test charge would be pushed or pulled. Um, so I'm going to switch boards. Okay, right. So I'm going to switch boards. Okay, so field lines represent, so continuing where we were. Field lines represent vector quantities, right? That's what I'm trying to say. There's still, these lines are representing vectors as in magnitude and direction, but they don't do it the way arrows do it. We no longer have a concept of length, you understand what I'm saying? So direction is still represented by arrow orientation. Whichever way the arrow is pointing in a line is the direction of that line, but the lines can curve now. So the direction at any given point near a curve or at a curve would be captured by a line tangent to that curve, just like tangent line, just like derivatives, same idea. Um, and how is field magnitude represented now? Okay, by the density of lines. The closer the lines are, the stronger the field. How do I know that, or why is that, or what does that? And I literally mean the number of lines per unit area on the page. Why? Oh, because if you look, well, yeah, see, like in our original vector field picture from a point charge, when we were drawing vectors, the smaller the vector meant the weaker the field. And so as you got farther and farther away from a point, the arrows got smaller because we know that the field must be getting weaker. Why do I know that? Because inverse R squared, because the field Coulomb's law, field equals constant times Q over R squared. So as you get farther away, it has to be the case that the field strength gets weaker. So when you're drawing vectors, you can see that in the length of the vector. Once you sew up the vectors and you make the lines like this, then we no longer have length. But you can see in the picture, in the simple case on which this is all based, it's all based on one point. As you get farther from that point, the lines do get more spread out, right? They get less dense. There's literally a greater number of lines per unit area close to the Q than there is like far away from the Q. So, and if we were drawing everything to scale, if I were more careful and more precise, then you could literally assign, there would literally be a proportionality constant where the number of lines per unit area on the page could directly map or correlate to number of newtons per coulomb, like in space. So from here on in, orientation of line indicates direction, and density of lines in a certain region of the page indicates strength of field in a certain region of space. Okay, so again, I'm saying in the right when Andy brought up the word density, like That's not a random word. Like that's not just a cute observation or whatever. That's actually crucial to the reading and writing of these field line pictures. Density of lines, number of lines per unit area on the page. Now, from here on, or in your mind, or on computer screen, number of lines per unit area, like square centimeter on computer screen, now indicates strength of field in region of space depicted, represented by that place on the computer screen, if that makes sense. All right. So what I'm gonna back up now and be more rigorous about this sort of. Like here's how what I want to tell you now is like how you draw a field line diagram. And not that you're going to draw a million of them. You have to draw some sometimes. I'm not saying you're going to spend the rest of your life drawing field line diagrams and or writing, and this would be how to draw them by hand or how to generate them, with computer software. I'm not saying you're going to do this all the time, but it, but if you understand what the rules are for how they're drawn, then you use those same rules to know how to interpret them, how to read the field line diagrams. So the rules are actually fairly simple. First, you choose a scaling factor, like I mentioned before. Like you could say, I'm going to draw 8 lines, 8 field lines for every 1 coulomb of source charge. Or if it's more abstract, if you're not literally dealing with numbers, if you're dealing with like ratios and like those Google images were, you could say 8, for example, you could say I'm going to draw 8 field lines for every Q worth of charge, of source charge. And then if I somewhere there's a place of 2Q, then I'll draw 16 lines, etc. So you make a scaling factor, and then you're going to stick with that scaling factor throughout your whole drawing or any other drawings that come with it. I mean, through your whole diagram or any other diagrams of the same situation. So you choose a scaling factor. Then you start drawing lines by hand or by computer. You start drawing lines, and here's how you do it. You start every single line at a positive. The truth is that's what you just do. You start drawing lines out from the positive, and you draw them as symmetrically as you can. You draw them out of that positive the way you would if the positive were just by itself somewhere, like our original thing 2 weeks ago. So one of the reasons I pick 8 as an example, 8 is just an example, but 8 is nice, as you notice, because 8 is like an asterisk, is like sort of the minimum number needed to kind of show a radial pattern unambiguously, right? So if you had a positive Q somewhere in your picture, you'd start drawing lines coming out of that positive Q. And you would draw them radially like this, the way they would be complete if that were the only thing in your picture. Then, so you start all your lines at positives. And then, well, I'll get back to second. Then that's 2A. I'm going to go back to that page in a second. Oh, sorry. Oh, no. Oh, sorry. No, this is the right page. So every line, so you're going to start a bunch of lines at your positive. Then any lines that are going to end at all are going to end at negative. So you just start drawing lines from the positive to the negative, as in the picture that I just showed you a minute ago, right? So that's pretty simple so far. But in that picture I just showed you, it was equal and opposite charges. I'm going to show you a couple more pictures in a minute, if we have time, where there's no, or like the situation we had 2 weeks ago, you might have like a positive 3Q source over here and a negative 1Q source over here. Like there's no rule that you have to have an even distribution of charge that's creating field. So what do you do? So yes, every line that you start, you're going to start at positive, and then every line is going to end at a negative. But what if more lines have to come out of that positive than can come into the negative? Like, well, then lines can come from or go off to infinity, which means the edge of the page. So lines, all field lines, either start at positive or come in from infinity. Again, I'm going to show you an example in a minute. And all field lines either end at negative or they go off to infinity. If you're like me, which I hope you're not, but if you're like me, the reaction I had when I first heard that in college, I was like, what are you even saying? Like, okay, they either start at positive or they come in from infinity. Like, as opposed to what? Like, didn't you just cover all the possible, like, what are you even saying? Note what we're saying is that no line will ever just start in the middle of the page or end in the middle of the page. Again, I'm saying lines don't have length as such. If they have exactly the length they need to get from positive to negative, or if there's more lines coming out of a positive or more lines going into a negative because the negative is like stronger charge, then lines will come in or go out from infinity. But what they won't ever do is originate or terminate in the middle of space. In other words, the only thing that can cause field is charge. Field is the indication to space over here that there is charge over there. If there's no charge, there's no field. Their field lines do not start or stop spontaneously. Okay, so back to drawing. So you're going to sit down and draw a field line diagram. First, you're going to pick a scaling factor, like, okay, for every coulomb of charge or every Q of charge, I'm going to draw 8 lines. Okay, so then say you have a positive Q over here and you have a negative 2Q over here. So you would draw like 8 lines symmetrically coming out of that positive Q, and you would draw like 16 lines, because if the negative is twice as charged, you would have like 16 lines coming in to the negative. And every single line that came out of the positive, you would join over to the negative. And then all the remaining negatives like would come in from outer space, from infinity, right? But then like how do you connect them or what like okay, so we're almost there. Like, just like you start at positive, you end at negative, you do everything sort of as evenly as you can. But then how do you connect lines or how do you get from here to there? Well, it's actually simpler than it might seem. The bottom line is that field lines, as we observed in the pictures, can bend and curve. They can. They are the summation of a bunch of vectors, but they are not vectors. So field lines can bend or curve, but what they cannot do is cross. What field lines are, so that's a rule. You can bend field lines, but you can't cross them, like ever. Why? Why can you not cross them? For the same reason that you can bend them. Because what the field lines are a representation of net field effects. Like the field lines that you're drawing, what you're trying to capture is the summation of all of the contributions from all the different charges everywhere that are creating this field. Again, like we did 2 weeks ago. So the point is that you might think, wait, isn't a line coming in? There's a line coming in from this positive over here, but then there's like a different line like coming down toward this negative over here. Like, aren't they crossing? You might think that. And at first it might seem that way. Like, so this guy is doing something and this guy's doing something. So aren't the lines crossing? But the point is the vectors are crossing. But then with the original vector arrows may be intersecting. But then you add them together to get the resultant vector. That's the calculation we did 2 weeks ago. And the resultant is the thing that's being sewed up and combined into one big line. These lines, in other words, they represent net effects. The lines represent net electrostatic force per charge due to every bit of source material that's creating that force. So in other words, even though at first glance you might think certain things should cross, what the lines actually are the pattern that you get at the end of the day after you've crossed everything and added everything together. So nothing can cross at the end of the day. The crossing's already been done, if that makes sense. If you're still thinking that lines are crossing when you're drawing something, it means you're not done drawing, in effect. So field lines, so the only rules we have so far is you pick a scaling factor, lines start at positive or come in from infinity, they end at negative or they go off to infinity, and then they can bend and curve, but they can't cross. With those 3 rules in mind, then all you do is draw the smoothest, simplest, most symmetric pattern of lines that you can that obeys those three rules. Like, I mean, it sounds very vague in a way, but it's not. Like the point is, and I'll go back and show you again what I'm saying now with the Google image pictures. Every one of these pictures is just that. It's a smoothing out. It's a standing back and looking at the pattern that all the individual field vectors would have created if you originally had a whole bunch of arrows and you stood back and looked at how are the arrows trending. These are like the trend lines of all the arrows being connected up. And there's only one way to do that once you follow these. If you follow these rules, if you allow bending but not crossing, if you always start at positive and end at negative, then you're going to get a bunch of lines that do a certain thing. Um, you'll know that you now again I'm saying it takes a little getting used to, but it's like a Newton's law free body diagram. Like, and again, I'm not trying to, I mean, everybody's a different person. But when I was first studying this stuff, I thought free body diagram, like I never knew how they were drawing free. Maybe sometimes I did, but I certainly didn't know how they were drawing component diagrams. And it always seemed, well, I don't want to get off the topic, but the point is this, that I thought that the free body diagrams were something that you sort of could only understand or really draw with confidence once you had already solved the problem and you knew everything that was going on with the forces. I thought it was like a teacher trick where they went back and sort of just drew a diagram to capture everything they had already figured out. But that's not the case. The case is that if you actually follow the rules of drawing a free body diagram, then the diagram makes itself for you. Like you just follow the rules of the picture and then you have the picture and then the picture forces you to solve the problem correctly. Like that you may or may not be able to relate to that. But it's the same thing here. At first, it looks like these field line diagrams could only be drawn by people that already understand what's going on and then they retrofit their pictures. But in fact, once you get used to drawing or reading these pictures, there's only one way to do it. And by following the rules of doing it, then you start seeing what's going on. So, and I'll show you that and one way to know. So what it's saying right here, one way to sort of check, and this again does sort of relate back to the thing that Annie was saying before, is that a good indication that you're probably doing your diagram somewhat correctly or understanding your diagram correctly is that as you get farther and farther away from the charges, the source charges in the piece of paper, the patterns should be getting less and less intricate, less and less complicated. The patterns should be getting more and more uniform because the farther and farther away you're getting from the charges, the more you're just getting into distant empty space. And in empty space, there's no field, right? Or like the field is as simple as possible, right? So, number one way to understand, one way to check that you're doing things right is that field lines should get increasingly uniform as you get farther from the charges. And the other way to check, or the other observation to make about these field lines and field line diagrams is that every field line picture, again, they look intricate. I keep using the word intricate because they are intricate. Like there's like a lot of lines involved. Again, please remember that every line that you look at is like a whole bunch of arrows that we didn't draw. So like they're intricate, but they're a lot simpler than a whole bunch of arrows. They're intricate, but they're just intricate enough to show you a pattern that the arrows would be following. And that pattern is just that. It's always some kind of pattern. It's always an interplay of symmetry and asymmetry. Symmetry means sameness. Asymmetry means difference, right? What I want to say, and then we'll spend the next 6 minutes just looking at the pictures again and just trying to see this. What I'm trying to say is that the field in the first place, field is information at one location of space indicating the specific properties of an object that occupies some other point in space. That's the whole notion of the field, is that if a proton is here, all of space knows it if a proton is here, because remember, we believe now, and why do we believe this again? Because we see all the time that a proton can pull on an electron even without touching it, and can push on another proton even without touching it. And more to the point, we know that a proton pulls on an electron even with like across empty space, protons pull on electrons, and they don't just pull vaguely. They pull in a precise numerical way that numerically depends on exactly how big the proton or the bunch of protons is and exactly where it is in relation to the other electrons, right? So somehow the information of a proton over here exists at a point in space over there. And that's what we call the field. And again, we're not literally saying that there's literally an arrow sitting there or literally a line sitting there. We're saying that there is information sitting there in space, information of magnitude and information of direction. The best way we can picture it in our mind, or the best way we have discovered so far to picture it in our mind, is with these lines. It's a representation. We don't, right? But what is it representing? The fact that whatever is happening in space over here is known is accessible to space over there. And the pattern of the lines is meant to show the pattern of this magnitude and directional information, these forces waiting to happen in space. So the way it does that, so what it says in blue here, and again, I'm going to switch the screens for the last 4 minutes, and you'll just see what I'm trying to say. And then that's it. But what I'm trying to say in the blue up here is that field lines are the difference that make a difference. Field lines over here show what's going on over there by the extent to which they are asymmetric. Asymmetry, this is what I mean by the difference that makes a difference. Field line diagrams are only as asymmetric as the charge distributions that cause them. If there was nothing in space at all, space is perfectly symmetric, there'd be no lines in space, it'd just be a smooth space. You put one dot in space, like one proton, and now you get a bunch of lines in space that follow a pretty symmetric pattern, almost as symmetric as lines can get. They'll all like burst out like rays from a sun, right? They're as symmetric as it gets, symmetric the same in every single direction. But they're all coming from a certain point. So they indicate that that point, that proton is there at that location. The more complicated the situation you create, the more complicated the charge distribution, the more asymmetry you're putting in space, the more asymmetric the lines will become. So very I know we have 2 minutes, and I'm not saying anymore, I'm putting down the cannoli, but like I'm just trying to say, going back to, if I can, sorry. Like, yeah, like, oh, a perfect example to end on. And I know we have 2 minutes. And again, please forgive but like, right. If you just look at these four pictures right here, notice, I mean, they're different, right? And they're intricate. They look like they're hard to draw in a way, but if you stare at them for a while, you see that each one of them is the only way you could have drawn it for the situation that it is, if you just follow the rules that I'm saying. And if you look at, for example, uh, like the top left picture, it's two positives, right? So the lines are so they were so they're pushing everything away from both of them. But clearly the right hand positive of the top left drawing, the right hand is a stronger charge than the left source. You could tell because more lines are coming out of it, right? So there's an asymmetry in the lines in the sense that there's an asymmetry. Oh, it even says in the top, but in the sense that there's an asymmetry in the charge distribution. But it's only as asymmetric and weird as the charge distribution itself is. So the lines are always in the smoothest possible pattern they can be, because it all starts with the premise that space would be perfectly smooth if there was nothing in it at all. Do you follow it? So I'll end on that. It's 4:20. So we'll see you in 2 days. Hopefully that sort of makes sense. See you in 2 days. And I won't have more exams in 2 days because I travel, but I will keep coming. They'll keep coming though. Sorry. Uh,
Bye, thank you.
thank you. Thank you. Sorry. Bye. Okay. And I'm ending.